Hello, everyone. Today we will be exploring the kinematics transport theorem in greater detail. I think this is a concept that we all kind of take for granted, and I hope that by going through the derivation and a few applications of this equation, you all will gain a better mathematical and physical understanding of this theorem. So, just a refresher, the transport theorem works on 3D vectors. It relates the time rate of change of a vector observed in a certain frame to the time rate of change of the same vector observed in another frame. And the time rate of change of the vector is observed to be different between the two frames if one of those frames is rotating with respect to the other. So let's take a look at this phenomenon in action. So I made these two animations to illustrate this. Pretend that we are here in the inertial frame, the black frame. At a displacement ROB from us is a frame V, and this frame is rotating with respect to us. There's a point P that's bobbing back and forth in the B frame, but to us, it looks like RBP is undergoing some kind of bobbing back and forth plus some kind of circular motion. Now let's travel over to frame B. So we're spinning with frame B now. Since we're spinning with frame B, our BP only appears to be bobbing back and forth and not rotating. You can see that if we go back to the inertial frame, there's this extra term in the velocity that accounts for the circular appearing trajectory of our BP's rate of change. Now we can try to derive the transport equation. So let me just freeze the time here. Okay, so we've frozen the time, and now we have two reference frames to work with. Go back to our... So we can begin by resolving the RBP vector in the inertial frame basis, and we want to denote that by subscript I. We can resolve that same vector in the B basis, and we'll denote that by subscript B. So we end up with the same vector, but represented in terms of different unit basis vectors. So let's take the time derivative as if we were in the inertial frame. We are inertial frame observers. Remember that even though we are in the inertial frame, we can still use frame B's basis to report what this RBP vector is. We can apply the product rule, and since scalars only have magnitude, their rates of change are not time dependent, so we just put a dot on top of them. But we run into a curious problem. Since frame B is rotating, as observers in the I frame, the basis unit vectors of frame B are time varying. So let's figure out what this derivative is. Frame B has a circular motion relative to us, so we can say that in a time delta t, the basis vector of B will have traveled an angle of delta theta. The difference between the B hat vectors is denoted as delta B hat. And I put a subscript I here in the delta B hat for consistency, because if you were in the B frame, delta B hat would appear to be 0. If the time increment is infinitesimally small, delta theta approaches d theta, and the basis vector of frame B, or the rate of change, or I'm sorry, the change in B hat would become dB. And note that since this triangle formed by B hat, dB, and the new B hat has an angle d theta which is approaching 0, these two angles will approach 90 degrees. Hence, B hat is perpendicular to dB, and dB has a direction of this way. So we can write dB as its magnitude times its direction. Since omega is coming out of the screen, you can use the right-hand rule to represent the direction of dB. And of course, you unitize it by dividing by this magnitude here. Since the time step traveled is infinitesimally small, the arc length that's traveled, which is magnitude of b hat times d theta, is approximately just the magnitude of dB. So we write this as that. And using the cross product identities, we can write the denominator here as this. And we end up with this equation here. Now, all we have to do is use engineering math, the kind of math that infuriates every mathematician. We can, quote unquote, divide both sides by dt. And since d theta over dt is just the magnitude of omega, this term cancels out. And we find that the inertial frame derivative of a unit basis vector of frame B is just the angular velocity of B relative to I cross that unit basis vector. So now we can go back to our original derivation and substitute in these derivative of B basis vectors. Since the cross product is distributive, we can group together these terms and we end up with our final equation. Note that this term here is exactly what the person spinning with the B frame sees, right? Because he or she only sees this bobbing back and forth, the x dot, y dot, and z dot along the B basis vectors. And this term right here is exactly RBP. Note that in this derivation, I wrote everything in terms of the B basis, but this theorem still holds for any basis resolution. You can even mix up the unit vectors. So here's an example. In the inertial frame, the cannonballs once fired appear to travel straight since there are no external forces. However, to someone in the B frame, rotating with the B frame, the cannonballs appear to curve. This is very applicable to aerospace engineering. Okay, let's say you're trying to fly from the North Pole to the South Pole in the shortest distance, which is a geodesic. Someone at the North Pole is in an inertial frame since he or she is on the Earth's rotational axis, and everyone else, including us, is spinning with the Earth. So we are in the B frame. To the person at the North Pole, the airplane will appear to travel along the geodesic as planned. However, to us, the airplane will have appeared to have taken a curved path. The airplane will appear to take the green path to us. If you're in the northern hemisphere and you look up, the airplane will have appeared to veer towards your right. And if you're in the southern hemisphere, the airplane would have appeared to veer towards your left. This is the Coriolis effect caused by Earth's rotation. In addition, if you're in charge of designing this flight path, you would have to take into account the Earth's rotation. If you naively design the plane at t equals 0 to fly directly from the North to South Pole in a straight geodesic, the airplane will actually end up taking the green path and veer off course. I hope this presentation has helped you all understand the transform theorem in greater detail. And thank you to these creators for creating the nice videos. And yeah, thanks for watching.